Guys, it's getting late. I'm getting tired. I think this is the perfect time for a cheer. What do you say? Are you with me? 1, 2, 3. I feel good. Oh, I feel so good. Let's go now. All right, so where were we? Area of a plane region. We're going to use circumscribed rectangles now. I said we could go over the top with this stuff, right? So we're going to go over the top right now. And we're going to have that same function, f of x, which is continuous on the closed interval a to b. And then we're going to divide it up into n rectangles of the same width, delta x, which actually is going to end up being b minus a all over n. And then what we're going to do here is we're going to know that there is some point, at least one point in this closed interval x sub I minus 1 to x sub I that would map to the absolute maximum height. So we're guaranteed that by previous work that we've done. And notice that f of d sub I, the height, times delta x is going to be the area of the ith rectangle here. So f of d sub I times delta x is the area of this ith rectangle, and f of d sub I being the maximum height is going to leave extra area there, which we really don't want. So it's going to be above the x-axis, and as you draw that out, so we know that the sum of the areas of the n rectangles here is actually going to be bigger than or equal to, and in this case strictly bigger than the area, the actual area of everything underneath. So what I do know is the sum of the n rectangles is the sum I equals 1 to n, because I have n of them, of the a sub i's, so the area of all n rectangles. But what I can do to find the area then is I can eliminate this excess area that's over the top of it by taking smaller and smaller and smaller rectangles, which means more and more and more rectangles. So simply I'm just going to take the limit as n goes to infinity of the sum I equals 1 to n of the height times the base, which is f of d sub I for the absolute maximum height, times the width or the base of delta x, which once again, delta x we know is b minus a all over n if they're going to be the same width for all n rectangles. So now what we're going to do is we're actually going to look at a specific example to come up with an exact area of something that's very awkward here, which is the y equals x squared graph. Now we know that f of x equals x squared is continuous. We know that it's on or above the x-axis from 0 to 3. And we know that when you plug in 3 you get 9. But if I plug in pi, I get pi squared, right? So the question is, what's the exact area between the x-axis and f of x equals x squared when x ranges from 0 to 3? Well, let's find out. We know it's continuous, so that's not a problem. And we're going to use the circumscribed rectangles because in this case it works out a little bit easier for us. The other reason is because that's actually what we did when you guys decided you wanted to go over the top over there after your cheer. So here we go. First of all, I'm just drawing one rectangle. I'm drawing the ith rectangle here, and I need to find its area. So I need to find a sub I, the area of this green rectangle. Now as you notice, I'm actually going to have excess area here that I don't need. So all this green stuff on top is actually bad. This is extra area. And of course I drew a big rectangle, so this looks like maybe I only had 4 rectangles. So I'm going to take more and more and more rectangles and squeeze that error that's over the top out. So this delta x, once again, is going to be the ith subinterval is x sub I minus 1 to x sub I. Remember, I ranges from 1 to n, so the left endpoint is actually x sub 0. Is 0 in this case, and the right endpoint of 3 is actually x sub n. That's going to be the nth endpoint there. But anyway, delta x is b minus a divided by n. Of course, b minus a is 3 minus 0, and I don't know how many rectangles. If I wanted 4 rectangles, my width would be 3/4, right? But it's going to be 3 over n is going to be my delta x, that's my base, times my height. Now what I really need to find here is what the maximum height is. Well, what do you know about y equals x squared? You know that from 0 to 3 it's an increasing function. That means means is you go left to right, it actually goes uphill. So the maximum height is actually going to occur at the right endpoint. So x sub I is actually going to equal our d sub I, which yields the maximum height. So f of d sub I is actually f of x sub I, the right side of that ith interval. So what I need to do now then to come up with the a sub I, the area of this entire rectangle, not just the area, but the whole thing is going to be the base times the height. So a sub I is actually going to equal f of x sub I, because that's going to be the height, right? The right endpoint yields that height, times delta x. So I'm going to keep going here and try and figure out what this is here. So first of all, to find out what f of x sub I is, well, f of anything is that anything squared. I didn't write that, but that's, I guess I did up here. So f of x sub I is x sub I quantity squared, but that doesn't really help us figure anything out. What we need to know is how far over x sub I is. So let's think about this. I'm going to draw another rectangle here. If that was my first rectangle and the left end point is 0, which is x sub 0, the right end point would be x sub 1. The question is, how far over would I be? Well, I'd be 1 delta x over, right? For the second rectangle, I'd be 2 delta x's over to hit that right endpoint. For the third one, I'd be 3 delta x's over. And so ultimately, I need to know what x sub I is in this case. So for x sub I, I'm going to actually be I times delta x over. So for the ith rectangle, whatever that is, if this was the second one, I would be, so if the width of my knuckle is delta x, there's 1 delta x and 2 delta x's, that would be x sub 2 down there. So the right endpoint is actually the number of delta x's over as the number of the ith interval. So it's going to be I times delta x to the right. So that's what delta I delta x is actually equal to x sub I. So let's figure out what that is. So delta x was b minus a all over n, which is 3 over n. So it's I times 3 over n, or 3i over n. So that's going to be x sub I. And then so f of x sub I is going to be that thing quantity squared. So it's this thing quantity squared. So it's 3i squared, which is 9. 3i quantity squared is 9i squared, all over n quantity squared is n squared, and then times delta x. Okay, and so delta x, once again, was 3 divided by n, and then so what I can do is I can kind of shuffle this together, make this look a little bit nicer, and this is 27i squared all over n cubed, and that is going to be the area of the ith rectangle. So then what I'm going to want to do is I'm going to want to add up all of these rectangles and then take the limit as n goes to infinity. So I'm going to come over here to do that and hope that I don't mess this up for you, because I'm sure like me, you're ready to be almost done with this. So what we're going to do is we're going to come up with the area then is going to be where I take more and more and more rectangles. So that's going to be the limit as n goes to infinity of the sum I equals 1 to n of the areas of the ith rectangle. So basically that's what that is in general. Now let's put down what this is actually for us, is the limit as n goes to infinity of the sum I equals 1 to n. And instead of a sub I can write in 27 I cubed over n cubed. And I'm going to write it like this. It's 27 over n cubed times, sorry, I squared. I'm not sure if I said I cubed or I squared, but it's times I squared there. And so what varies here? N is a constant. N is a specific number. So if I have 10 rectangles, n is 10 and n cubed is 1,000, right? So it's something specific. It's some specific number. What varies here is I. So the variable I changes from 1 to n as you go here. So what I can do here is consider this a constant, and I can pull the constant down in front. So you remember our theorem that we had, and I'm going to wait till the end to take the limit, but the sigma of a constant times a function is the constant times the sigma of the function, right? So once again, I haven't taken the limit yet, so this is the limit as n goes to infinity of, now it's going to be 27 over n cubed times the sum I equals 1 to n of I squared. Now all we got to do is remember our theorem that says what the sigma of I squared when I ranges from 1 to n is. So this is going to be the limit as n goes to infinity of 27 over n cubed times, and I'm going to put this in brackets here, but for I squared, what was this again? This was n times n plus 1 times 2n plus 1 all over 6, right? So we have this. Now I'm going to wait on the limit, but basically what I need to do is just simplify this here and then let n go to infinity. So if I do that, what I'm going to do quick is I'm going to multiply through on the top here and try and step this out so I don't lose you. But anyway, if I multiply these two together, it's 2n squared, but then I'm going to have to multiply everything by n. So it's 2n cubed, right? And then plus 2n plus n is plus 3n, but then times n is plus 3n squared, and then plus 1, but then times n again is going to be plus n all over 6. So that's ultimately what the top part became, is 2n cubed plus 3n squared plus n, if you multiply all that out. And then before I take this limit, I'm actually going to want to try and simplify this out here. So what I'm going to do is I'm going to switch the n cubed with the 6 first. Okay, I'm going to switch those out, and this is going to become the limit as n goes to infinity of 27 over 6. Of course, 27 over 6 is going to cancel down a little bit, so that's actually, if I divide that by 3 and that by 3, I get 9 and 2. So this is 9 halves times, and then I'm going to put the n cubes with these other n's in here, and I've got 2n cubed plus 3n squared plus n, and it's all over n cubed, right? But instead of taking the whole thing divided by n cubed, I'm going to just divide each part by n cubed, because what I want to do is evaluate this in a way that allows me to take the limit. So what I notice here is that n cubed and n cubed cancel, and I'm left with 2 for that one. And then here, n squared and n cubed cancel, and I'm left with an n in the denominator. And then for this last one, n cancels with n cubed, and I'm left with 1 over n squared here. And so really what I have here is I've got the limit as n goes to infinity of 9 halves times that thing. So let me just rewrite that. That's the limit as n goes to infinity, once again, of 9 halves times, this is going to be 2 plus 3 over n plus 1 over n squared. Now what I can simply do is I can let n go to infinity, and if I let n go to infinity, so I'm going to come over here, I'll erase this. I think we're safe now. I don't need that for later. But now I'm going to let n go to infinity and evaluate that limit. And if I do that, let n go to infinity, of course, limit of a constant times a function is the constant times the limit of the function. So the 9 halves comes out front times the limit of the sum is the sum of the limit. Limit of a constant is a constant. So it's going to be 2 plus, as n goes to infinity, 3 divided by n goes to 0, and 1 over n squared goes to 0. So it's going to be 2 plus 0, which ends up being 9 halves times 2, or 9 square units. So I'm going to put u squared for square units because I don't know what my units are for the measurement. But the area of this thing is actually 9. And let's just look at kind of what that looks like. So here's my best interpretation, not being very good at art at all, although I heard there's a lot of math in it, just not the math that I know apparently. But anyway, so there is the area, which is a shape that we don't have a geometry equation for, but by using, in this case, circumscribed rectangles, and knowing that the max height would occur at the right endpoint, and then figuring out how far away that right endpoint is, then we could actually use that along with the definition here to know that the true area underneath that curve is exactly 9 square units between 0 and 3 for f of x equals x squared. And now we can go do whatever you want.